All right, let's look at another trick with multiple integrals, change of coordinates and Jacobians. So what this is, it's really trying to recapture the magic of, think of U sub or trig sub, right, back from Calc 1, Calc 2. These were two of our most powerful techniques of anti-differentiation, right, techniques of integration. They were both changes of coordinates, meaning what? You had an integral that used to be an integral dx, and then, you do something and it becomes an integral du, right? Or trig sub. You had an integral that used to be an integral dx, and then you do something, and now it's an integral d theta, right? And the way that we're going to set up our change of coordinates in Jacobians, it's going to be more like how we set up trig sub back for single integrals, more than how we did u sub. It's sort of, I mean, they're equivalent, but just the way it gets written, it's going to look a little bit more like trig sub. And here's the idea. Remember back when, if you did in trigonometric substitution, say you wanted to let, x equal tangent of theta. So this is sort of a little flashback, right? Say x was tangent of theta. Then what would you do? You would take a derivative, right? You'd get secant squared, and then you could apply this change of coordinates to your integral, right? Once you knew that dx was secant squared theta d theta, right? Because you could say, then you could apply it to an integral. Say you had this, you wanted to take an antiderivative, you get 1 plus tangent squared theta, and then dx becomes what? Secant squared theta d theta, right? So if you look, there are really two things that happen. One is you're replacing x by something else, right? The other thing that's happening is the dx, changes to d theta, but it's not an even trade. There's this extra thing you need to multiply by. And this is essentially the Jacobian. We didn't call it that back in Calc 1 or Calc 2, but that's essentially what this is. It's that extra, it's that price you pay for the change of variables, right? It's the scaling factor between dx and d theta, right? And it's calculated by doing a derivative, right? So now here, how does this look? What we're going to do is we're going to generalize this for two variable scenario, right? So in general, we're going to say if you have, see now we don't just have x as a function of theta, but we're going to have x as a function of two variables, and instead of theta, I'm going to use u and v for the new variables, right? So that's x, and then you'll also have y, right, because we're doing multiple integrals, and y can also become a function of two variables, u and v, right? So if you want to make this change of variables, right, if you want this change of variables, right, this change of variables, so just like we wanted to plug tangent of theta into the single integral, here we have some function f of uv that I want to plug in for x, and some function g of uv that I want to plug in for y. This change of variables corresponds to what? Jacobian. So the Jacobian, right, which is going to be some function of u and v. I mean, it could be constant, but in general, it could be a function of u and v, is a certain determinant, right? So it's the determinant of its partial f with respect to u, partial f with respect to v, partial g with respect to u, and partial g with respect to v, right? It's the determinant of that matrix of partial derivatives. So, if you look at what was happening before, see this Jacobian in the one-dimensional case was just this, right? It was called theta instead of u, but that's exactly what it was. It was just that top left corner, right? But now with this extra variable, now it's a 2 by 2 matrix of derivatives as opposed to just one single derivative, right? So this is how we do a general change of variables. Okay, so let's then try this technique out, right? Let's do a change of coordinates using a Jacobian. And what is this? This is maybe a familiar problem if you've been watching this playlist, right? In a previous video, we did We used Fubini's theorem to get the area of this parallelogram. Let's do the same problem again, but we're not going to use Fubini's theorem. Instead, let's use change of coordinates. To find the area of a parallelogram, right? So let's do this instead. So let's see what happens here. Here, if we do this region, right? What is this region R? So let's just briefly sketch our region here. Right, so we had y equals x, right, from 0, 0 to 2, 2. We had y equals 3x minus 4 from 2, 2 to 3, 5. We had y equals 3x from 0, 0 to 1, 3. And we had y equals x plus 2 from 1, 3 to 3, 5, right? So this was our parallelogram. And I want this area, right? So now, what can I do to get this? Well, think of, essentially, we want to somehow strategically change coordinates. I want to convert all these x and y locations into u and v locations, right? I want some new coordinates that'll let us visit this, all the points in the same region R, right? But cleaner, right? I want to set this up so this is cleaner. So one nice way to think of this is you could imagine this as picking new axes, right? So you could say, you know what, I would really much rather that I had an axis here, like maybe this could be our u axis, right? And then maybe this could be our v axis. Right. So then then you can kind of look and say, well, how do what formulas would give me these, right? Because that's a nice geometric intuition, but it doesn't really tell us what the formulas exactly should be, right? So how could you get those? You could say, all right, well, what is this u axis, right? Well, the u axis, that should be the place where v equals 0, right? Well, what equals 0 along that axis? Well, actually, y minus x is 0 along that axis, right? So if I want to define that axis, maybe actually v equals y minus x. That might be a good relation. See, I'm just kind of lining those two ideas up, right? I'm saying along the u-axis, v equals 0, and just like on the x-axis, y equals 0, right? And then what else is 0 along that axis in terms of x and y? Well, y minus x is 0. Okay, so maybe v equals y minus x. That might be a good relationship. Right. Now, same thing here. U is going to equal 0 along the v-axis. What else is 0 along the v-axis? Y minus 3x would be 0 along that axis. Therefore, u, just line those up. U should equal y minus 3x. Okay, so now, what do I have? Now I have actually a really nice region that this corresponds to, right? Because what is going on here, the point, you could plug in these points now to get u and v points, right? Like 0, 0. So look at this. Look at this change of coordinates. Right? Take this and put x equals 0, y equals 0 into it, right? So at x equals 0, y equals 0, right? What do you get? You get u equals 0, right? Just subbing in those zeros. And you get v equals 0, right? So what that's showing us is that the origin goes to the origin. The origin stays at the origin, right? Then let's plug in 2, 2. So what do we get there? We get a new point. Here I get 2 minus 3 times 2 for u. And I get right? So I get -4 and 0, right? That's what I get for that 2, 2, right? So I actually get a point that looks like this, -4, 0, 0, 0, right? And we can keep going, right? Let's plug in our next point here, right? What's our next point? Let's do 3, 5, right? What are we going to have? We're going to have u equals 5 minus 9 is -4, and we're going to have v equals 2, right? So that's going to put us up here, right? -4, 2. And then our last point is what? It's going to be at 1, 3, right? At 1, 3, what do we have? We have u equals 0, as it should have, right? And then I'm going to have 2. So that's this point here, 0, 2. Right? So here's what's so nice about this change of coordinates we just did. This goofy parallelogram we used to have now becomes a rectangle, right? This is so super nice, right? So this new region is really a lot nicer than the old region, right? So let's call this S, right? So if you look, you know, this kind of awkward region R, right, got transformed into a really clean region S, right? This, in the UV plane, it's just the box that has, you know, U between -4 and 0, and V between 0 and 2, right? So the new domain is really clean after we do this Jacobian, right? After we do this change of coordinates. All right, and also we should address, how do we know in between that why are these straight lines? Well, one way to think of it is they used to be straight lines, and we applied a linear transformation, therefore they're still straight lines. You could also plug in more points in between. You could also use formulas to get them, right? You could plug in a whole formula instead of just coordinates, and you would see that the formulas do come out linear. So let's now proceed to calculate our Jacobian. So notice here, we're kind of backwards right now. Like, it was more intuitive to pick the change of coordinates, u and v, as functions of y and x. But if you look up here, I actually need x and y as functions of u and v. So I need to invert this transformation, right? So let's do a little bit of algebra. Let's turn this around, right? Let's take this and let's solve for x and y. Right, so like that bottom equation, I could add x to both sides to get that y equals v plus x. And then I could sub that in. Wait, let's see. I'm trying to get. Oh, here, no. Sorry, easier thing to do. Just subtract the equations, right? Because that'll cancel y. Right, so just subtract the equation. So we get u minus v equals, then the y's cancel, and then I get -2x. There we go. It's just, you could do what I was about to do. I was going to do substitution, but here it's just a little cleaner with elimination. So, so that gives us then x becomes what? X then is u minus v over -2, or you can say that x then becomes -1/2 u plus 1/2 v, right? There's x. See, now this is that f of uv, right, that we were talking about up here. See, that's x as a function of u and v. Okay, and now let's get y, right? So now that I have x, now we can plug in to get y, because now, see, y then is v plus x. So now add x to v to get y. So this will be what? V plus minus 1/2 u plus 1/2 v, right? So combine like terms, and we get y. So now y is going to be negative 1/2 u, right, plus 3/2 v. And there's that g, right? This is g of uv that we were talking about up here. Okay, so now I can do the actual Jacobian, right? So this is going to tell me what I multiply by. So my Jacobian in this case is going to be the determinant of what? It's going to be the determinant of, I'm going to take the partial with respect to u of that top formula, right? And then partial with respect to v of that top formula. Then I'm going to do partial with respect to u of the bottom formula. Partial with respect to v of the bottom formula. Now, these partials come out actually very clean. They're all linear functions, so the partials are just constants. Right? So what do we get for our Jacobian? Here we get negative 3/4, right, minus negative 1/4, right? So we actually get negative 3/4 plus 1/4 becomes negative 1/2. So there's my Jacobian. Now here it ended up being a constant. It doesn't have to be constant in general, right? It could be a function of u and v, right? Here, because the formulas were linear, the Jacobian ended up a constant. So there we go. There's our little Jacobian. Now we're actually ready to do this, right? To do the integral where I multiply by the Jacobian, right? It's going to be a double integral, but it will work, right? So now I can evaluate. I'm ready. I have all my. So evaluate the double integral. Using this Jacobian. Right, so what is it going to be? Well, this double integral becomes the double integral on a new region, S, right? And when I go to S, it's not dx dy anymore, right? Now it's du dv. Remember to put your Jacobian in here, right? This is where you put your Jacobian. Now in here, if there were x and y's, right, you would sub, x equals, these formulas. X equals negative 1/2 u plus 1/2 v, and y equals negative 1/2 u plus 3/2 v. You would sub in for x and y if there were any x's and y's there. You would do that, but there aren't any here. It's just a constant function, right? So you don't have to do any substitutions. So, but it still affects the bounds, and it still affects that. There's that Jacobian there, right? So now, take this Jacobian, right? And it's just a constant, so you could factor it out. And you could set up your integral now, right? So u goes from -4 to 0, right? V goes from 0 to 2. It's the integral of 1 dv du. Let's see. Just want to make sure we're... Yep, u is going -4 to 0, and v is going 0 to 2. Yeah, that's right. Right, so then... now we can plug all this in, right? And when we do this, oh, you know what? Sorry. The it's technically u equal 0 to u equal -4, right? Because if you look at where those bounds came from, right? They came up in that order, if you look at with respect to the original bounds, like the order that those points came from the x coordinates. So, yeah, so it's actually this way. There we go. Which is kind of it, and that's why our Jacobian came out negative, because there was that reflection, like this parallelogram. Here it got reflected into quadrant 2, so it kind of got distorted into a square. It got flattened out a little into a square, but it also got reflected, and that's why the Jacobian was negative. It was kind of showing us that there was a reflection. So then, if you want, the negative sign can flip your bounds around. There we go. And so then what happens? Well, what is this, right? If you look at this is just the area of a rectangle, right? And you could do the double integral if you want, or you could just say it's the area of the rectangle, right? Because this is just length times width times height, right? On a 1 by 2 by 4 box is all that is, right? So this is just 8, which means our answer is just 4, right? Which is a third way that we've solved this problem, right? So we did it in a previous video. We did it with Jacobian's theorem, and we did it with vector geometry with the cross product formula. Here we did it with a change of coordinates. Right? And notice here, you could calculate the integral, but you could also geometry your way out of it, which it's always easier to, if you can ever do it with geometry, go for it. Right? So there we go. We got 4 once again for that same problem, the third time. All consistent, all very nice. All right, thank you so much. Jacobians will come back more. You'll see plenty more examples of Jacobians in the coming videos.